If I may use this opportunity, you mentioned that Weber's electrodynamics also allow for the kind of to study the electromagnetic radiation, right?
Yes,
Right.
yes.
How do you connect it? I don't see, if, right.
Yes. Yes, that was made, that's amazing because you see, Weber together with Gauss, they did build the first working telegraph. That was in 1833. There is even a commemorative plaque at the Observatorium in Göttingen where Gauss worked about this invention of the telegraph. And 24 years later, Weber and Kirchhoff, they were the first to deduce the telegraph equation. Both of them working based on Weber's electrodynamics. So we have a wire and many particles. And so this many-body system, they could solve this equation. With Weber's here I talked about the two-body problem, but they solve a many-body problem. And then they deduce for the first time in the history of physics the complete telegraph equation, which is the wave equation plus a term which is proportional to the resistivity of the wire and which makes an exponential decay of the signal. But then when the resistivity of the metal is very small, then we go back to the wave equations. So Weber and Kirchhoff, that was in 1857. 7 or 10 years before Maxwell made his first paper on the waves. And so Weber deduced the wave equation from his fourth law. That's just amazing, completely forgotten in the textbooks as well. But it is there, it was published. And Kirchhoff's paper in particular, it was translated in the same year. It was published in German. Weber and Kirchhoff, they did publish in the Annalen der Physik, just like Einstein many years later. But the Kirchhoff's paper of 1857, Jan, it was also translated into English in the Philosophical Magazine. And Maxwell was one of the many who did study this paper. 1857. His equations are from 1864, 7 years after that. And his book is from 1873, almost 20 years after that. And so, or 15 years. But this paper by Kirchhoff was, so it was a deduction, and Kirchhoff even studied the reflections of waves in this telegraph and the decay and so on. And then he has a second paper in which the wire has some thickness, and he shows how the signal goes inside the wire. It is just amazing. So it was already available in German and in English in 1857. And he worked independently from Weber, but both of them utilizing Weber's fourth law. And Maxwell knew that. And all the others, Kelvin, and because it was, and Weber had just measured 1 year before his constant C. Because this work by Kirchhoff and Weber was theoretical. So they obtained the wave equation and the velocity, which was C. And the value of C had just been measured by Weber, 1856, and found 3 times 10 to 8 meters per second. So the connection with light, electromagnetism and light, was already by the measurement of this constant. And then the next year they obtained the wave equation based on Weber's electrodynamics. No fields at all. Everything is unknown. In the textbooks, we read the textbooks and we open, oh, Maxwell then introduced his displacement current, and then he obtained his wave equation.
Right.
So
If we go to kind of wave equations in the Maxwell theory, kind of, right? So then you have wave equations for electric and magnetic field, and also for the potentials, right? But in this relational kind of electrodynamics, the wave equations are...
They are for the current, for the surface charge in the wire, but also for the potential. We can also deduce that because Weber has conservation of energy, so you can deduce a potential from Weber. So you also have an equation for the potential there.
Oh, very nice.
But specifically for the currents, intensity of the currents and surface charges.
Very nice, interesting. So that would be also a subject of the Kuhn's presentations,
Yes,
right?
I look forward for that.
Right. So, shall we? Okay, please. So I will read the question, right? So what is the opinion of speakers on Einstein's statement expressed in his book Sidelights on Relativity 1920, where he says in page 16 and 23, space is endowed with physical qualities. In this sense, therefore, there exists an ether. According to general theory of relativity, space without ether is unthinkable. For such space, there not only would be propagating of light, but also the possibility of existence for standards of space and time. Right.
Can you go
Right.
ahead, please?
I think that would be another very deep presentation related to Michelson-Morley experiment and the rejection of the ether idea in back in that was the end of 19th century, so
yes.
1898 or something like that,
yes.
right? So I think it's very well known that Einstein also admitted later that I think I even read the paper somewhere that the rejection of the ether idea was too premature. That was a kind of so. And nowadays we have a big development in the field of Higgs bosons and so on, which is also the field which fills the ambient space everywhere and so on. And that's also the reason that we have the interaction of a particle with the Higgs field, the particle gets their mass and so on. So I think my opinion is that the ether kind of idea is might be a subject of re-examination in future, certainly, right? And I don't know whether you have...
I agree completely with you, Jan. I only don't like this statement by Einstein that space is endowed with physical qualities, because to me, just empty space has no properties. I would say that maybe there is a medium in space, and this medium has some properties, but not space itself. At least that's my way of thinking.
It goes actually back to what you already mentioned, Ernst Mach and his kind of Mach principle, that that was an attempt kind of to get rid of the notion of the absolute space as it is in the Newton physics.
Exactly. But you see, and also going a little back in history, Weber himself, just like Maxwell, he did believe in an ether. His force law is a direct interaction between particles. But the Weber's ether, different from Maxwell's was a continuum. So, and abstract these electric and magnetic fields. No one knows what a field is. They have different definitions. Even Maxwell, Faraday, Einstein, and the textbooks, each one gives a different and many different definitions of what a field is and so on. But while the ether of Maxwell was a continuum, the ether of Weber was like a plasma, many positive and negative particles moving around, okay? Just like a plasma in a tokamak or and so on. But the interaction between any two particles would be his force law. But then, so that in this medium, it would be the possibility of waves, disturbances in this medium. And these disturbances, this perturbation would at light velocity. But the properties would be of the medium, not of space, empty space. To say that space can be curved, time can be... So I myself, I don't like any of these ideas. They don't appeal to my physical intuition.
Thank you. So the next question is quite simple, right? Okay. When a direct current is turned on and travels through a wire, is that wave transversal or longitudinal? Right, so you want to start?
Yes, that depends on how you are formulating your problem. So there is one solution based on these field quantities, the electric field, the magnetic fields, and so on. And then we need to go to Maxwell's equations and solve it. Another solution, as you asked, Ian, is that we consider that from the point of view of Weber's electrodynamics. Then we have only the interaction between the electrons and the lattice. For instance, the positive lattice is fixed in the wire and the electrons can move around, either like a direct current or they can just vibrate around positive nucleus and so on. And so we need to study these different solutions. I think that in general there will be both possibilities, transversal component and longitudinal component. Both of them should appear in Weber's electrodynamics. In some special case, we might have only one, only transverse or only longitudinal, but in general, we might have both of them.
Right. I would also maybe add a little, I think I totally agree with you that there is this notion of Poynting vector, right? So which is kind of used to explain how the electromotoric force is kind of transported, right? But, right, so this is, I think I found very intriguing that there are papers, even nowadays, kind of, I have some papers from 2012 and so on, where people are still discussing, you know, how the Poynting vector and so. As you said, I totally agree. The notion of the fields is somehow it's slightly confusing. You know which field is the source and what field is kind of consequence of that the other field and so on. So,
and also in this question, it is interesting as well. There is another very important topic which Weber was also the pioneer. Is that when we have, just like this question, a wire and a current, even a constant current in a resistive wire, so that according to Weber's electrodynamics and according to measurements as well, there will be a distribution of surface charges on the surface of this copper wire, for instance. And for a DC current, a constant current, the surface density of charge will be constant in time, but it will change along the direction of the wire, the magnitude. And so, and this distribution of surface charge will give rise to not only a magnetic field, but also an electric field, if we talk in terms of field theory, okay? And so Weber was the first to calculate the distribution of these surface charge, not only in a wire, but also in a ring, when we have a closed ring and a battery, and a constant current flowing there. These are just amazing calculations, and there are many modern experiments measuring these surface charges and measuring this external electric field. If we have a wire like that, the electric field will be like that, and the magnetic field will be in this direction. But also there will be an electric field, and we can map, for instance, these electric fields, which are based on this distribution of surface charges, with grass seeds. We just plant grass seeds, analogous with iron fillings, which map a magnetic field. Grass seeds or floor, you can map an electric field, and you see these electric fields which coincide with the calculations of Weber. That is just amazing.
Maybe just a small addition. I think people should not confuse the longitudinal waves, what we are speaking about in terms of the electromagnetic wave propagation, right? So it's slightly different topic. Right?
Yes,
so
maybe you could clarify a little bit. And so.
Yeah, that's related to the fact that if you write down the Maxwell equation and the related wave equation, so you will get the solution which is purely transversal, right? But what we are speculating here, kind of, right, is whether or not there exists also some other type of the electromagnetic wave propagating in the different way, as they are not transversal with respect to the direction of motion. Right? So I just want to, that's the kind of very important issue kind of this conference, right? So maybe I will read this comment that congratulations to Professor Assis for revealing some of the important developments of Weber's. I think
So
I'm also very thankful.
I thank this person who said these words, and I just ask once more for everyone who is watching me, just inform your students and colleagues about the English translations of Weber's works. If you do just that, that will be wonderful, because for 100 years, no one learns about Weber's electrodynamics in high school or at the university in physics or engineering, electrical engineering. We simply don't hear about that. We don't even know that there was an alternative electrodynamics. So if you just inform your students and your colleagues about the existence so they can read the original works, that can be, I hope it will be, a revolution for the 21st century.
Right. I like this question, if I may. Very interesting. Weber's conclusion presented by Professor Assis. Two particles with the same charge sign will attract each other at particle distance. Is that an experimental observation? I would say zillions of that.
Yes, because every atom is stable.
Right.
And to me, the stability of the nuclei is due to this property,
right,
not to nuclear forces. So we know that every atom, carbon, copper, everyone has or almost all of them, they are stable.
And the distance, the characteristic
And
distance
correct.
is 1 Fermi 10 to the minus 15.
10
right?
to the minus 15 meters. So the existence of all of us is already, to me, a proof of that. But what I would like to point out as well is that this property, it opens the possibility, and that's for new experiments like Professor Jan Rack and others they are trying now, is that with this property of Weber's electrodynamics, we can have a control of the inertia of the particles, of an electron. Because according to Weber, even for low velocities, the effective value of the inertial mass of a positron or an electron or any particle, the mass will not be a constant. It will depend on the distribution of charges around. So we can, I believe Weber's electrodynamics is the correct one. So in this case, when we apply it, we can have a control of a basic property of the electron, which is its inertial mass. And so this opens up a whole new fields of applications in electronics, in plasma physics, in tokamaks, and so on. And so that opens a whole new field of research and applications in solid-state physics. Effective, whenever anyone sees effective inertial mass, you can give a look. Certainly, I believe it will be Weber's law at work.
Right, and also the field of gravity, right? If
yes,
you can
sure.
manipulate it, right.
Because it is exactly this property that the effective inertial mass of the electrons depends on the surrounding charge, which is the origin of Mach's principle. That even the basic m of any particle is an interaction. It is not an intrinsic property of the particle, as Isaac Newton thought. I believe the correct one is the point of view of Ernst Mach, that the mass, the m of any particle, comes from a gravitational interaction with the distant universe. Not only the stars, but also galaxies. And the amazing thing, if anyone wishes, just give a look at a book on relational mechanics. And even this talk, I believe it is available, of 2019.
Right.
People can find it on the YouTube or so. Even these the basic inertia of anybody is already comes from a gravitational interaction with the distant universe, but you can deduce that with Weber's law applied to gravitation.
Right.
So,
and I love really this principle also from the point of view of philosophy, right?
Yes,
because
sure.
it gives you something like a holistic approach. Really,
Yes,
because
yes.
we are here, our masses and everything due to the presence of the whole universe.
yes,
right?
we are, everything is connected,
Right,
everything
right.
instantaneously with the whole universe.
Right, so let me, so that's the question. Professor Assis, can you talk more about Ampere's bridge experiment, right? That's
Yes.
very interesting question.
That's a
Right,
very
right.
interesting topic. I thank this person who made this question. Ampere, he began his experiments after Ørsted discovered that a current carrying wire deflects a magnet. And then Ampere said, maybe there are microscopic currents inside the magnet, and so we should have interaction between two current elements. Then later on, he made experiments with, for instance, two parallel wires that they attract one another. So this was the beginning of electrodynamics. Interaction between currents without magnets, okay? But Ampere went further on. He wanted to obtain a mathematical expression describing the force between two current elements. So he spent years making many experiments, and then finally in 1822 he obtained an expression for this force between two current elements, which this force does not appear in the textbooks. What the textbooks call Ampere's circuital law, the line integral of the magnetic field is proportional to the current which crosses the cross-section of the circuit. Ampere never wrote down this equation. Ampere never worked with the magnetic field concept. Ampere only worked with the force between current elements. And then in 1822 he obtained his final expression, which Maxwell said should always remain the most important formula of electrodynamics. But it doesn't appear in any textbooks of the 20th century. According to Ampere's force law, if we have two current elements which are along the same straight line connecting them, they should repel one another. No such a force appears based on Lorentz, Biot-Savart or Grassmann's force law. And this deduction that two elements along the same straight line flowing in the same direction should repel one another was a surprise to Ampere himself. That was a surprise. And then he said, can we test this? And then he made this so-called Ampere's bridge experiment, 1822 or 23. So we have here a battery, a switch, and a partial circuit. And here we have the bridge. So they are just like that, but the circuit is open. So we have a battery, the circuit with a switch, and here is something which can move. So it is a metallic bridge which is floating in two mercury troughs. Okay? Mercury is conductor. So it is just flowing there on the table. When Ampere closed the switch, a constant current began to flow around this closed circuit, and the bridge just moved forwards. So he made this experiment as a test of this prediction. And so to Ampere, that was a proof that this portion of the fixed circuit was repelling the portion in the bridge, because the two have currents in the same direction. In the other leg of the bridge, the same thing, because now the current is coming back. So the fixed one and the mobile one, current the same direction, they repel. So this longitudinal repulsion did make the bridge go away from the fixed portion. So that's amazing, because that was a prediction from his theory which was confirmed by experiments. And there is no such a force in standard electrodynamics. I spent, Professor Jan Rack knows this, that I spent 1 year back in 1980, 88, 89 in Boston, USA, working with Peter Granoux. He was a German physicist, experimental engineer, but he was working at the USA at that moment. He invited me and I spent 1 year there working with him. And he made many experiments about these longitudinal forces. There are other experiments, for instance, you can, if you have a very thin wire, when you pass a current through it, it breaks into many pieces. It's called the exploding wire phenomena. So there are many papers, just give a look at the papers by Granoux, Graneau. He is now, unfortunately, no longer with us, but his son, Neil Granoux, he works in Oxford. He has an Ampere laboratory, and he is also trying to perform many experiments, trying to distinguish Ampere from what appears in the textbook, Grassmann, Biot-Savart, and Lorentz, all related with these longitudinal forces. Maybe one day Professor Jan Rack we were talking just today before the conference about some possible experiment trying to distinguish Ampere from Grassmann.
Right, that is excellent idea. I think I also like to ask you, there were experiments kind of to try to prove that the inertial mass of the electrons can be changed with some of these frequencies.
Yes. So this is the same idea that if you change the distribution of charge around a test particle, its effective inertial mass will change. For instance, a special case is when we have a spherical shell with uniformly distribution of charges, and inside it we have a test particle. So according to standard electrodynamics, there is the potential inside the shell is constant, there is no electric and no magnetic field. So if I make an oscillation with an electron here, then if I surround it with a charged shell and make a vibration, nothing will change according to standard electrodynamics. But according to Weber's electrodynamics, if I make a vibration here, the frequency of vibration will depend on the inertial mass of the test particle. If I now surround the test particle with a charged spherical shell and make the same experiment, the frequency should change. And so there are nowadays some experiments which are beginning to test this prediction. That's a different prediction between Weber and Lorentz, between Weber's electrodynamics and classical electrodynamics. So after 150 years, it's great that now people are doing real experiments with Weber. Not only theoretical calculations, but real experiments. But we are just in the beginning, after 150 years that it was completely forgotten.
Very nice. There is another question. What do you think why the work of Weber, Coulomb and Ampere were overwritten by Bohr? It was amazing that Weber made this up all in his head. Where did he get the knowledge from? Yeah, that's...
I believe that was just based on his mathematical solution of his two-body problem. And then he found that two charges of the same sign, they would attract if they were very, very close. And then he had this Kepler's idea of Prague, that the electrons around should move in elliptical orbits and so on. But the first part, can you go back, I don't know, to the previous question? I don't know if... yes, what they were not only overwritten by Bohr, but they were completely forgotten. As I said, what appears in every textbook as Ampere's circuital law, Ampere never wrote such a thing. What Ampere obtained was a force law between two current elements. No fields, no line integral of magnetic field, no flux of magnetic... Never. He never worked with the field concept.
And never with partial differential. Right?
Yes, and so... But you see, and then he obtained this force law between two current elements, which predicts this repulsion in this case, which always complies action and reaction. The law that we learn in the textbooks by Grassmann, Biot-Savart, does not comply with action and reaction. And Maxwell knew the laws of Ampere and Grassmann. The law of Ampere is 1822, the Grassmann is 1845, a mathematician of Germany. And Maxwell knew both of them. In the textbooks nowadays, we in physics or in electrical engineering, we learn only the force of Grassmann, which nowadays we deduce from the so-called Lorentz force law. The Ampere's force law does not appear at all. And so Maxwell knew both of them, and he made a comparison, and he said, of these equations, that of Ampere is undoubtedly the best, and must always remain the cardinal formula of electrodynamics. Nowadays we say that we follow Maxwell's ideas, but we simply kept out of the textbooks the force of Ampere. Because, why is the reason? That's why I come back here. Because it's not compatible with Lorentz. You cannot deduce the force between current elements of Ampere from Lorentz. From Lorentz, you deduce only the Grassmann or Biot-Savart force law. And with Weber, on the other hand, you deduce only the force law of Ampere, but not that of Grassmann, Biot-Savart. As nowadays everything is based not only on Maxwell's ideas, but also on Lorentz and Einstein's special and general theories of relativity, everything which is not connected with Lorentz is kept out of the textbooks to avoid questions from the students, maybe. But so that's the reason why I think that it's because it would cause many problems. So you see, the works of even Coulomb, every textbook talks about Coulomb, but his works never translate into English. But now they are, in the last 10 years. Also Ampere, his whole book has been translated and commented from French to English. And now the works by Weber. So this paradigm can now come back alive again from the originators, which were Newton for gravitation, then Coulomb for the force between charges, Ampere for the force between current elements, and Weber for the force between particles in relative motion. So this action at a distance paradigm can come back to life to fight against the other one, and hopefully to bring new technological developments. Thank you.
That's the essential, I believe. So, can Weber equation accurately describe the size of the atom based by describing the orbits of the electrons?
I know about the size of the nuclei, about the size of the orbits, then that we need to make the calculations and so on. But there are, in principle, many possible orbits with different distances. But I don't know who made this question, but you see, Weber's model with these remarkable predictions, also the prediction, they are very remarkable. Weber's model is very simple because his particles had only mass and charge. But nowadays we know that every particle, even the simplest one like an electron or a proton or a positron, they have also a spin. So they are more complicated than Weber's model. So I believe that if we, for instance, try to begin to work with Weber's electrodynamics, giving not only the mass and charge of the particle, but also the spin. So if they have spin, they are not simple. So even an electron must be composed of parts, and it must spin. Sure, even the name spin is that. The textbooks say, oh, you should not think about that. But I do think and I believe that spin is just rotation. Maybe two particles around one another, maybe many particles. But if we then, it's a more complicated model. So we have maybe two particles spinning one another here. That would be an electron. Then we have the nuclei here with two positives. Then we could see these orbits. Maybe there will be some resonance frequencies and so on that might lead to the correct order of magnitude for the size of the orbits of the electrons. Maybe this quantization. But we see the development stopped 150 years ago. But now we have so powerful computers who can do this mathematical and many softwares, numerical calculations, and also so much numerical data from this nuclear physics. So we can make much more complicated, more real models of the atom. So we don't have all the answers, but the possibility is open.
Right, to include spin, it's, I think, you know, I don't know whether it's well-known fact, but in order to calculate the spin of the elementary proton, so to speak, in terms of the quantum field theory, QCD, it's still an open question.
Yes, yes,
so
it is.
Nobody knows where the 1/2 is coming from,
Yes.
right? In case of proton, for example, it's
Yes.
called the spin crisis.
So
right?
there are many possibilities for anyone who is watching us
Right.
here to begin to work. Not only theoretically, but also in the laboratory, trying to test it. So many different predictions and so.
Okay, next question. In the derivation of the negative mass, there are two charges but only one mass. Could you please specify to which charge does the mass belong to, or if its mass it's related to both charges? Thank you very much for the amazing talks. I think it's clear, right? So,
Yes. So there are two charges and two masses, because this is a two-body problem. So the particle 1 has mass m1, charge q1. Particle 2 has mass m2, charge q2. And so this two-body problem, they will orbit around one another with precession. And if they have opposite signs, if they have the same signs, they will be moving very close to one another. But both of them, they will be moving. And so you can just solve just like in Newton's problems. There are two masses and two charges. So later on, this person can give a look at this book on Weber's planetary model of the atom. So,
is there any idea what light, photons, could be in Weber's theory?
yes, as I said, Weber himself, he did believe in the wave theory of light. Just like every scientist at the 19th century, because of the interference experiments of many. But to Weber, this medium was composed of charged particles, which were around down there. And so there were too many body problem, not a continuum, no fields, not at all, just a gas of charged particles, positive and negatives. And even at one time in one of his works, he considered that this ether might be composed of charges of only one side. For instance, only electrons, we might say nowadays. That was just an idea. But so the photons, it's not specifically in Weber's mind. But we can think nowadays, as I said, when we have two particles, a photon might be my positive and a negative charge orbiting around one another, and this system might be moving at light velocity in the middle of this medium of charged particles. So possibilities, they are open, but we need to just try.
That's right. So, have you calculated RC for 2 electrons? I think it was done for 2 electrons, right? It's
Yes.
10 to the minus 15. And would such a situation be possible in nature? Yes. Could this relate to the phenomena of sustainable lightning?
Yes, that's a good question. But you see, the critical distance is proportional to the product of the two charges, 1 over r and 1 over m. And so 2 positrons or 2 electrons will give the same critical distance, 10 to minus 15 meters. So we don't know, up to now we have not found that in nature. But there are many mysteries in nature. For instance, the positive and negative charge, they look like symmetrical, just like the North Pole and the South Pole. But for some reason, in real nature, they are not so symmetrical. The basic particles that we normally have, the proton and the electron, they have different masses. They have equal and opposite charge, but different masses. We might have, for instance, an atom with a negative proton and a positron orbiting around, but we just have not found it. it should be symmetrical, but for some reason it's not so in nature. And so there are too many mysteries that we don't know. But
and the critical mass for the protons, if you...
Yes, it's possible. Anyone can just calculate. Just take the Weber's formula and plug in the mass of the two protons and two quarks, two gluons. So you can just play around. And so, oh, and there was a question of ball lightning. That's an interesting phenomenon that sometimes people say that they see it like a stable glowing ball with a plasma and so on. So that would be like a macroscopic system. So, but I'm not sure that this ball lightning has only one kind of charge. Maybe it is electrically neutral, positive and negative. So a complicated system, but the possibility is there that we can have stable systems with only electrodynamic forces based on Weber.
I have very good experience with this lightning balls, which once came to our cottage, you know, when I was a kid, you know.
In Finland?
No, in Czech here. So we have a weekend cottage, and the this ball came in.
Wow.
Look around, you know, how the rooms looks like, and then he
went away.
Went away, but with half of the cottage with him.
Okay.
Very good. So the next question is, how about the scalar magnetic field existence and modeling, right? So the question is whether the scalar magnetic, or there are different terms, you know, scalar, dielectric, magnetic, and so on field, whether this field exists or not. I think there is a lot of rumors for many years. They started from Tesla research, right? Mm-hmm. Tesla discovered something what he called radiant field, right? And then nowadays there are, I have forgotten the German professor Meyer, right? I think he was, he has even an experimental kit you can buy for 1,000 euros, where you can kind of experiment yourself with the scalar fields, right?
Very interesting.
Right. I have now forgotten the name. And so I believe that since Tesla, the scalar magnetic field is, to my opinion, known and it's proven, we have our own experiment in laboratory and so on. So
maybe you could tell a little bit about what kind of experiments are you trying?
I will have a presentation this afternoon about that.
Specifically,
so,
yes.
Right. So, and the modeling, I think we are at the beginning. To my opinion, this experimental field is, starting. There are also other groups worldwide who are also kind of studying the same phenomena using the Tesla transmitters and so on. I see that very fascinating, and so stay tuned for my afternoon talk. You know, so I will give more details. Very good. So thank you for your excellent talk and answer to the question.
Thank you very much for your kind invitation. Always a great pleasure for me to be here with you. A great friend and a great place to be. Thank you very much.
And I hope that we will stay in deep collaboration.
Yes, sure.
So thank you
very much.
And thank you all for watching.